The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So I'm going to give you a quick overview of where the technology is. Hopefully it will set the stage for the next 7 presentations. You at least will get some understanding of when the other speakers talk about systems, different systems and so forth, how the technology has progressed over the years. So this is the reason why we do what we are trying to do now. We have a serious situation in the US with repair rehabilitation of pavements. We'll be focusing much more on the concrete pavement side, but many of our pavements are very old, in need of repair, and we are just not able to do good repairs typically at night. We are not able to close our highways for extended period of time in large urban areas where you've got high volume traffic. This is a picture of the Seattle location, I-5. There is no way you can do any extended lane closure in a situation like this, Chicago, New York, any major cities. So we have been doing some quick repairs using rapid set concrete. It has not worked out very well. Sometimes it works well, many times it doesn't. So it's always a risky proposition when we use rapid set concrete. If you are doing short repairs, short lane closures, typically at night. If you want to do a good repair, then we have to do it right, have extended lane closures over several days, which we can't afford to do. So the solution is shorter closure, but also look at longer life treatments. When we talk about longer life treatments, we are doing many miles and miles of lane replacement. And basically, we are looking for service life of at least 30 to 40 years without having to go back and redo the repairs. This is, as I mentioned, this is a reasonably new technology. Concrete pavements, we are just coming up to 125th anniversary this year. The first concrete pavement or street was constructed in Bellefontaine. We've got a big celebration going on next Monday to celebrate that in Bellefontaine, Ohio. But just to give you where we are, so that we have been doing concrete pavements, cast in place 125 years. We have been doing precast concrete pavement 15 years, plus or minus, okay? But this is the only option many agencies have. So it's not a fad, something exotic. It is happening. It is being used on a production basis. It has been successfully constructed by different contractors without prior experience. And of course, we have availability of precast plants throughout the US. So this is a ready to be implemented technology. I'm not going to go through this, but we have been at it since about mid-1990s, trying to develop or improve the technology. We had done some work in the 50s and 60s in the US, but technology wasn't right. It didn't move forward. In Russia, they've been using precast pavements since the 1950s. In Siberia, they would ship panels, precast panels, because of the short construction season, and miles, hundreds of miles of pavements have been constructed using precast panels. In Japan, they've also used precast since about 1960s or 70s, but not at the scale that we are beginning to use in the US. There's been a lot of activities at the Federal Highway Administration level, highway DOTs, industry, and so forth. And about a few years ago, 2008 to 2012, there was a major study done under the Strategic Highway Research Program, and some guidelines were developed and so forth. And right now, we are in the process of implementing those guidelines and encouraging wider implementation by highway agencies who have not done much precast work, but do have the need for that, because everybody is facing this rapid renewal needs. And FHW is now supporting highway agencies with implementation, so-called wider implementation with financial support and with also tech support. So this is the background. We more or less started doing the production use since about 2001, used primarily for repair, rehabilitation. for longer lasting treatments. If you want few months service life or few years, maybe rapid set concrete might work. But if you are looking for longer, if you don't want to go and fix the fix, precast is a good option. So typically we are fabricating the panels off-site, transporting to the project site on the night of the construction or installation, and then it just requires some minimal field curing, few hours if you are using rapid setting grouts and so forth for what we call load transfer provisions and under the slab bedding requirements. Again, typically nighttime work, short work windows. That means we start lane closures at about 8 p.m. at night. We are open to traffic by 5 a.m. in the morning. Hopefully everything goes well. Nobody knows that there was some work done, okay, on that highway. So big concern is traffic. Is the traffic sufficient to warrant the use of precast concrete pavement? I may as well mention it right now. The precast concrete pavement is slightly more expensive than cast-in-place options, of course. When we do cast-in-place repairs of similar nature, the cost may be around $250 to $200 per square yard. When we do precast, we might be at $300 to $400 per square yard, depending on the project size. 2001, we started at about $900 per square yard. And over the period of time, because of competition, different systems being introduced, and the experience and the fact that the contractors are not taking too much risk now, the prices drop quite a bit to match the cast-in-place options. So is traffic volume significant? Is it heavy enough to preclude other pavement alternatives, alternate routes? Do we have options? Can we afford to close down I-94 here in Milwaukee and route traffic some other routes throughout the city or other options? Same way in Chicago and New York. The whole of California is like that. You just can't shut down any major highway in Los Angeles. Bottom line is there's only 8 hours to do that work, then precast should be strongly considered by agencies. So we've got two types of application, what referred to as the intermittent repairs and the continuous application. Intermittent repairs, we are basically doing full depth repairs or full panel replacement. And the continuous applications, we are doing miles and miles or hundreds of feet of replacement. A ramp replacement, a tollway plaza replacement, or again, miles and miles of damaged pavements, typically in the outside the truck lanes. The panels are always reinforced, or we are also beginning to use prestressed panels. And in the continuous system, we've got two systems, the jointed system and post-tension systems. Much more of the production work is right now with the jointed system, although California does use post-tension system. And again, we have reinforced panels. We do require reinforcement because of the lifting stress issues. So all the panels are reinforced, but we can also pre-stress or pre-tension the panels at the plant. Generic and proprietary systems are available, okay? So this is a view of what we are talking about. If it's an intermittent repair, typically instead of cast-in-place concrete, we are bringing the panel with dowel bars embedded or different systems. Forget this schematic, it's an older one, but we have different ways of providing for load transfer. Keep in mind, when we use precast panels, we always have to provide load transfer because we can't have smooth faces that will not be able to carry traffic over a long period of time. So we always have to make provision for what we call load transfer using typically dowel bars. When we are talking about continuous system, we are connecting one panel to the next panel. Again, different methods of load transfer provisions. Sometimes we have slats at the surface, sometimes we have slats at the bottom. Some systems are proprietary, some systems are generic, and I'll give you a little bit more discussion later on. So we've got two approaches now. This is a panel, so we can come in, place the panel directly on a prepared grade or base, rework base and prepared, so that's called grade supported, okay? Or if you don't want to be too worried about having a proper grade, we can finish the grade, leave a gap, and then the panel is supported on leveling bolts temporarily. We leave a gap, fill in the gap with a high strength bedding grout. That would be the bedding grout supported. And I'll give you examples. And typically the gap is 1/4 of an inch to 1/2 inch. And we may also then, once the panels are placed, we'll come back and do surface grinding if necessary, if the panel-to-panel joint elevation is more than 1/8 of an inch. Because this is all being used for high-speed application on interstate highways. We have speeds of 70, 80 miles per hour typically, and we want to make sure there's no elevation difference at the joints when we place these panels. The load transfer system, again, as I mentioned, we have to have load transfer from one joint, one panel to the other panel. We have two approaches, using slots at the panel surface, several variations, using slots at the panel bottom, one patented system, and I'll show you some of the examples. So this is a schematic of a panel placed on a prepared grade, and typically would use a bedding layer to provide some levelness. This is the schematic for panels placed using a leveling bolts and maintaining some gap, and we would come back and fill in the gap with a high-strength grout material, bedding grout, cementitious bedding grout. This is an example at LaGuardia Airport. You can see it was a demonstration project. We are using the leveling bolt approach. This is an older version of it. Workers typically place the plates and the panels with the leveling bolts are positioned on that. Since it was an airport, setting the panels at the right elevation, so there's a surveyor involved, we don't need to do that for a highway application. We go very quickly for the highway application using the levels of the adjacent lanes and so forth. But you can also see we can place the panels even in a rainy situation. So weather is not really a significant issue unless, of course, it's pouring rain and snow or something like that. This is the load transfer refinement. So we have indicated before that there are some panels with the slots at the bottom for load transfer. The other refinement is slots at the surface, typically narrow-mouthed slots. So we can even leave them in place before we fill in with the grout material or patch material the next night. So the narrow opening doesn't bother the traffic. The idea here is that we place the whole dowel bar, that 18-inch long dowel bar, in the slot. We place the panel in and then move the dowel bar into the adjacent panel, which may have a companion hole. Or if it's an existing pavement, we would drill a hole, epoxy, and so forth. So this is just a schematic of it. So the dowel bar is placed, the 18-inch or 15-inch long dowel bar, and then we slide the dowel bar into a hole, precast in the adjacent panel, or drill in an existing panel. The Tollway uses this concept quite a bit. They've made some modification, just allowed slightly wider opening for somebody to put their hand in, push the dowel bar in, twist it, so the epoxy in the adjacent panel in the hole is surrounding the dowel bar. This is a modification of that same concept, California design. So here we still have the same 18-inch long or whatever length of the dowel bar slot, except the opening is only in the back end. So once all the panels are placed, they would come in and slide the dowel bar into the hole in the adjacent panel, and then come back with the cementitious material or a polymer, polyester grout material, approved material, fill in the slot and the gap in the hole in the adjacent panel. This also shows the new leveling system that has been developed. So instead of having a Dayton Superior type anchoring system and positioning your 4 plates by hand, now the precaster is putting in the leveling system in the panel itself. So they take the whole leveling system, 4 locations within the panel, to the side, undo the leveling plate, push it down, and then use the screwing system to set the panel at the right elevation. Just some more views of that. So basically here you'll be sliding the dowel bar, setting the panel elevation using automated equipment, and this is where you would slide the dowel bar into the adjacent panel, and there's a gap maintained 1/4 inch to 1/2 inch gap. Then we would come back, and I'll give you, in the last presentation, in the second part, I have an example of a project, case study, where we go step by step for the different activities. So this is now some more improvement or modification or refinement to the technique. So here, instead of sliding the dowel bar into the adjacent panel, we just bring in a panel which has dowel bar embedded at one end, a slot at the other end, as shown here, and we are just going to come in and slide this panel with the embedded dowel bar into the other panel that has the slats. And different variation of the slat. On one project in the LA area, SH101, they used this shape of the slat. On the one project that's coming up, so in this project they have placed about 2,000 panels all over the LA area, Hollywood, that part. This project coming up, they'll be placing 7,000 panels over a period of 6 to 9 months. And they came up with their own version of the slat. The bottom line is you're still maintaining a narrow slat at the surface. This is the post-tension system, in the past referred to as PPCP, Prestressed Precast Concrete Pavement. So here we are basically bringing in panels. In the original version, the panels were single lane or 2 lane wide and maybe 8 to 10 foot long. And then we would be post-tensioning about 25 of them to give us a post-tension length of about 250 foot. Then an expansion joint, and we keep repeating the process. In this version, we are post-tensioning from the middle panels. In the next version, we are post-tensioning from the end panels. But in both cases, we have to deal with the blockouts, like here, for the pre-stressing operation. And that is considered as a possible future maintenance issue. So the current version, at least in California, they're post-tensioning from the side, from the end, and leaving a gap, and then using a precast panel to fill in that gap. And that's working out fine too. We are able to fabricate about 8 to 10 panels, depending on the precasters' facilities. If they are using a post-tensioning bed, the beds could be 300 foot long. They can do about 20 panels per night. Installation rate, if we are doing repairs, we are able to do about 15 to 20 repairs. Keep in mind, these repairs are spread out along many miles, so the operation is slowed down. We have to move from site to site. When we do the continuous placement, we have been doing 30 to 40 panels per lane closure per night. And so this lane closure we are talking about, as I mentioned before, we started about 8 o'clock. We start destroying the original concrete pavement, remove it. We may remove the base material, grade it, finish it, bring in some new base material, grade it, finish it, then bring the precast panels, also do the bedding, grout, and the dowel bars. Around midnight, we start bringing the panels. So we got about 4 hours to place the panels before we do the finishing activities in the last hour. So now the contractors are doing 6 minutes per panel, so 10 panels per hour. So if we have 4 to 5 hours after midnight, we're able to place 40 to 50 panels. And we need that kind of production rate. So depending on the panel length on this LA project, they were using 16-foot long panels. They're placing 50 at night, so we're doing 800-foot length of work every night, opening traffic in the morning. But the bottom line here is that because of the lag between production and installation, we need several weeks or months of panel production, depending on the size of a project. Hopefully in future, we'll be doing 1,000 foot, as I mentioned, in California, with the 50 panels, 16-foot length. They're already doing about 800 foot. So we are reaching at least a benchmark that I thought would take us a few more years to reach. So applications, primary, of course, high volume highways. Typically outside lanes, truck lanes, urban ramps. If you have a single lane ramp on a busy highway, from one busy highway to another busy highway, you can't afford to shut it down. This is one of your options. You can do a whole ramp or part of the ramp per lane closure within 2 or 3 nights. You can do the full ramp. Some additional applications, intersections, bridge approach slabs, underpasses, bus spades, airfields, still slightly lagging. We are not there yet. So intersections, if you have an asphalt intersection with a lot of rutting and so forth, that's a continuous maintenance issue for the highway agency. Many agencies are considering the use of precast. This is a project coming up in Mobile, Alabama. I'll be talking about it later on. But this is a completed project in the New York area. And speaker later on in this session, he'll be talking about his system that they've developed and is quite widely in the New York, New Jersey area and other states. But that was his system used with the slats at the bottom. So you don't see any joint-related slats at the surface. But bridge approach slabs, if you have to repair the bridge approach slabs overnight, this is a method to do it, to take care of bumps or cracking in the approach slab. Many agencies are beginning to use that. And Steve will be talking about application at the Illinois Tollway in the Chicago area in the second part. So just some details about how that bridge approach slab might work. Typically you are redoing the seat here a few nights previously, but basically you need lane closure just to take care of the seat reinforcement. This is the Fort Miller system with the slide at the bottom. You can bring in and place the panels with the slide position over the reinforcement that anchors the new approach slab onto the bridge abutment. But again, different variations exist on how to do the anchorage. It doesn't have to be the bottom slide. There are generic systems also available. Bus pads, if you have an asphalt bus pad that keeps having problems, you can go in overnight and take out 100-foot long, grade it, put in the panels, come morning, it's a new bus pad, hopefully a longer lasting bus pad. So basically what are we looking for when we use precast concrete pavements? Typically we say for repair applications maybe 15 to 20 years, but again we are rethinking that, because if we continue to do continuous repairs on a pavement, before you know it we will have replaced most of the slab areas with precast panels. And maybe we should be designing for a longer time, and the long time would be 40 years. So this is basically what we are looking for, a 40-year service life whenever we do anything new on our pavements. When we design new concrete pavement, construct new concrete pavements, we are looking at 40-year service life. And that's what we are expecting out of precast, just because it is slightly more expensive, but we just don't want to go back and keep doing the fix on a very high volume highway. Some technical considerations. I'm just going to finish up very quickly. Basically, we have the same requirements for most of the system. We've got many different systems, but it's the jointing and load transfer and the support condition, that's where we see the differences. This just to show that when the panels exceed certain size, length or width, then we are basically looking at higher lifting stresses, and we would have to pre-tension or pre-stress the panels before taking them to the site. So once typically we are over 20-foot length, either in the width or the length, we are doing pre-tensioning at the plant. Just views of panel fabrication. I'm just going to go through it because I think I'm exceeding my time. Very straightforward. These are reinforced panels. You're using slump concrete. We are doing the regular testing at the precast plant, doing the finishing. Then within 16 hours, the next day, we are stripping the forms, lifting, and then doing the finishing work on the panels. This is the pre-stressing bed. Here in California, they got pre-stressing bed, let's say 300-foot long. They can do 20 panels with a single set of strands. They don't have to place reinforcement 20 times. And then they come back and cut off the strands. They can also do steam curing. Quickly, support condition, we are basically popping. Most of the time, we would have to just lift up the concrete panel, damaged panel, and do some minor finishing work and place a new panel on it. Sometimes we have to redo the base, typically an old cement-treated base or lean concrete base, and then we may use a new rapid setting lean concrete base. This is what they do in California quite a bit. Most of the other states, they are just using the existing base, granular, or trimming a cement-treated base and going with that. Just some quick examples. Again, most of the work is done at night. This is I-66, a ramp construction. You can see work starts at about 8 o'clock with taking out the concrete. We are preparing the base, doing tie bar, whatever we have to do to tie in with the adjacent panel, finishing the grade, using a bedding layer, bringing the panels, and this is the completed section. This is another one. I'm just going to quickly show this. The reason I'm showing this is in the urban intersection that was converted into concrete, but this is what I wanted to point out. So if you have utility that you have to take care of, manholes and so forth, you can build in these locations within your panel. Panels are precisely located and positioned and surveyed through surveying and so forth. So, and then just come back and do some quick rapid set concrete around these locations. I hope this has given you a quick overview of what the technology is or where we are heading. In the next sessions, we'll talk about some of the specific projects.